rule with a power function, where that power function is my outer function. Second case tells us how to find the derivative of e to a function. Well, last week we talked about how to find the derivative of e to the x. The derivative of e to the x is just e to the x, right? And so to combine that with the chain rule to find the derivative of e to a function of x, we have to do the derivative of the outside evaluated at the inside, so e to the g of x, times the derivative of the inside, g prime of x. Likewise, last week we talked about finding the derivative of b to the x. That's just the natural log of b times b to the x. To find the derivative of a composite function where b to the x is the outer function, it's just the derivative of the outside evaluated at the inside, the natural log of times b to the g of x, and then chain rule tells us we have to multiply by the derivative of the inside. Likewise, last week we talked about finding the derivative of the natural log of x. The derivative of the natural log of x is 1 over x, right? And so to find the derivative of a composite function where the natural log is the outer function, it's just going to be 1 over the function. So 1 over g of x times g prime of x. Some people remember this as g prime of x over g of x, whichever makes more sense to you. Whatever works for you, use that. And then the last one, the derivative of log base b of g of x. We know the derivative of log base b of x is just 1 over the natural log of b times 1 over x. We are dealing with a composite function of x instead of just x, so that would be 1 over the natural log of b times 1 over g of x times the derivative of the inside, g prime of x. Okay, so some people can look at that box at the top, and that's all they need to be able to use the chain rule. Some people like to remember these specific cases. Over the past couple of years, I've discovered that some people, it helps people to even kind of break it down more than that. And so if you need to break it down more than that, I'm going to do the following for the first couple of examples. I'm going to actually name, right? So last week I actually named, when we were using the product rule or the chain rule, I gave a name to the first function and the second function. And I kind of went off to the side and I found the derivative of the pieces. We can do that with the chain rule too, if needed, right? So that's not necessary, but if it helps you, we can totally do that. So if we're viewing it as taking the derivative of O of I, so it's going to look a little funny, but the O stands for the outside, the I stands for the inside. So, and again, this d over dx is just saying I'm taking the derivative with respect to x of what's on the inside. So the chain rule tells us we're going to take the derivative of the outside evaluated at the inside, so O prime of I, right, times the derivative of the inside, so the inner function is what I'm calling I, so I prime. Okay, so really 3 different ways of looking at this. In my personal opinion, it's a lot of work to go through and define O and define I, but if that's what you need to do to be able to use the chain rule appropriately, then do it. Okay, so I'm going to do that on the first couple of problems, but then I won't write as many details later on. Okay, so let's go ahead and take a look at this first problem. Okay, so the biggest thing is being able to identify that we need to use the chain, right? So these functions can be mixed in with all the functions that we talked about last week, and they can be mixed in with products and quotients, but being able to recognize that we need to use the chain rule is really one of the hardest things. So make certain that you're always verbalizing what it is we're dealing with. So if I look at this function right here, f of x, if I tried to put it in words, what am I dealing with? I have this function raised to a power, right? So I have this function 7x squared plus 9x plus 4 raised to the 10th power. So we should hopefully very quickly be able to see, okay, well, last week we talked about finding the derivative of x to the 10th, right? Now, instead of finding the derivative of x to the 10th, we're taking the derivative of a function of x raised to the 10th power, okay? And so that tells me that my outer function is basically what I'm doing to that inner function, and that inner function is being raised to the 10th power. So I'm going to identify my O, right, as x to the 10th, right, because that is what I am doing to that inner function. My I, my inner function, is that 7x squared plus 9x plus 4. Okay, and so then I need the derivative of these two functions to be able to plug in to the chain. Okay, so if I take the derivative of x to the 10th, the derivative of x to the 10th is what? 10x to the 9th. Okay, if I take the derivative, I'm going to write it as I prime. The derivative of I prime, we're dealing with a sum of three functions. I can just find the derivative of each piece and leave the sign in between. The derivative of 7x squared is 14x, plus the derivative of 9x is just 9, plus the derivative of a constant by itself is just 0. So I could write plus 0 or leave that off. Okay. And so if we look at what the chain rule tells us, we need to find the derivative of O and evaluate it at I, and then we need to multiply by the derivative of I. Okay, so we already see here that I prime is 14x plus 9. But we need O prime of I. Okay, so O prime of I just means that we need to plug in my function I for every occurrence of x. I'm evaluating my derivative function at 7x squared plus 9x plus 4. And so I'm just replacing every occurrence of x with my I, right? So that would be 10 times 7x squared plus 9x plus 4 raised to the 9th power. Okay. Green on green. This is probably not going to work out very well. Y'all can't see that when I do that, can you? Okay. Underline. Okay. And so this is my O prime of I. All right, so to find the derivative, I need to take the derivative of the outside, evaluate it at the inside. So that's 10 times 7x squared plus 9x plus 4 to the 9. And this is my O prime of I. And then I need to multiply by the derivative of the inside. Derivative of the inside, I prime, is 14x plus 9. And so this here is I prime. Okay, so again, there is no need to involve all this definition out to the side if you are getting the chain rule. Okay, so if you get the chain rule, you could just hopefully write what I have boxed here. Right, but this out to the side is just to help you if you are really struggling to see the components of the chain. Okay, so any questions on the answer or what I have going on out to the side here? How are we feeling about the chain rule? Like, are we not good? Okay. Does this help out to the side? You like the chain? You don't like the chain? Okay. I was telling my kids when I left tonight, I'm like, I'm going to go teach the chain rule. I'm so excited. They thought it was crazy. Yeah, so it comes from the fact that we're using the power rule, right? So if you're looking over here, hopefully what I have in this box right here is familiar, right? Because it's what we did last week, right? To find the derivative of a power function, the power comes down in front and we subtract 1 from the power, okay? And so this is the derivative of the outside, but then we need to evaluate the outside at the inner function. So then we plug in, not going to work very well, but we're going to plug in the inner function for x. You're welcome. mean, so you have to be able to identify what is the outer thing, right? So the outermost thing here is your raising something to the 10th power, right? And so you see that I'm dealing with a function raised to a power. If you don't like what I did off to the right, you can just realize, okay, I'm dealing with a function raised to a power. All right, that tells me I'm in case 1. Right, so if it helps you, you could just remember the cases and say, okay, I'm in case 1. So to find the derivative, that power is going to come down in front, right? The 10 comes down in front. The inner function remains the same. I subtract 1 from the power, and then I multiply by the derivative of that inner function, right? So you can think of it. Oh, go for it. You're welcome. No, you're fine. So yeah, so you can remember the chain rule in general, or you can just remember these 5 specific cases, right? So you're not going to have to use the chain rule for anything other than these 5 specific cases. And so you just need to identify which of the cases you're in, and then remember what form it's going to take. Lots of different ways. You just have to figure out what works for you. Other questions? Okay. We're going to be doing a lot of it tonight, so if it doesn't make sense yet, we're okay. All right, so number 2, g of x is equal to 5e to the negative 5x squared. Okay, so again, we recognize a function that, it's almost a function we could take the derivative of last week, right? What would it have to have been if I could have to take the derivative of it last week? 5e to the x, okay? So recognizing what it is I knew how to take the derivative of last week, that tells me what my outer function is, okay? And so here, 5e to the x is my outer function, and then I am evaluating that function at negative 5x squared, okay? So my outer function is 5e to the x, and my inner function is negative 5x squared. Okay. If you struggle with seeing that, realize that if I wanted to evaluate my outer function at negative 5x squared, that just means that I would plug in this negative 5x squared for every occurrence of x. So I'd plug in negative 5x squared for that x. And so when you have it written like this, it's easier to see, outer and inner, right? It's a composition function where the outer function is O and the inner function is negative 5x squared. So we need the derivative of both. So O prime, the derivative of 5e to the x is just 5e to the x. The derivative of my inner function, we have a constant times a power function. The constant stays out in front, that power comes down. We have negative 10x because we bring that power down and then we subtract 1. So I prime is negative 10x. But then we need to evaluate the derivative of the outer function at the inner function. So we need O prime of I. And so then we plug in the inner function for every occurrence of x. And so my O prime of I becomes 5e to the negative 5x squared, right? So I'm just plugging in my I for x. And so that's here. Plugging in our I for x. Okay? And so then we come over here. We know that the derivative is the derivative of the outside evaluated at the inside, which is what we have right here. So g prime of x is the derivative of the outside evaluated at the inside. And then we have to multiply by the derivative of the inside, which here the derivative of the inside, I prime, is just negative 10x. Okay. So again, that works out to the side, identifying your outer function and your inner function. You can use that. Or, look, if we look back up at the specific cases, which of the specific cases am I in here? 1, 2, 3, 4, 5. 2, right? So we're in specific case 2. And so we know the derivative of e to a function. We have this constant out in front, but we know that if we're finding the derivative of a constant times the function, the constant stays there, so 5 stays there. And then the derivative of e to a function is e to the function times the derivative of the function, right? So you can remember it, identify it by just looking at which special case we're in, or you could go out to the side and identify your outer and your inner, whatever works best for your brain. Okay? Questions on 2? Questions on, in general, questions about chain? We just see a whole lot of it and start to feel better. Okay, so h of x is equal to log base 7 of 2x to the 4th minus 3x plus e to the x. Okay, so again, we have to recognize that we are dealing with a composite function. What function is similar to this that we could have found the derivative of last week? Log base 7 of x, right? We knew how to find the derivative of log base 7 of x last week. So we see we're now dealing with log base 7 of a function of x. So we're needing to involve the chain rule. Our outer function, O, is log base 7 of x. And then our inner function is 2x to the 4th minus 3x plus e to the x. Okay. So we need to find the derivative of each of those. We know the derivative of log base 7 of x, that's 1 over the natural log of 7 times 1 over x. I think some people remember that a little bit differently than me. You could write that as 1 fraction, 1 over the natural log of 7 times x, or you could write it as 1 over x times the natural log of 7, whatever makes the most sense for you. I prime, we see I is a sum and difference of 3 functions, so we can just find the derivative of each piece and leave the sign in between. 2x to the 4th, that is a power function, so we can use the power rule. That becomes, the 2 stays out in front, and then that 4 comes down, so we have 8x cubed minus the derivative of 3x, it's just 3. And that's because that's a power function. So we have the 3 out in front, and then the 1 comes down, and then we subtract 1 from the power. So it's really 1x to the 0, which that whole thing becomes 1. So we really have 3 times 1, which is just 3, plus the derivative of e to the x, which is just e to the x. Okay. So then we need to evaluate our O prime at our inner function. So we take our inner function, and we are going to plug it in for every occurrence of x in our outer derivative. Okay. So we have 1 over the natural log of 7 times 1 over 2x to the 4th minus 3x plus e to the x. And so then our derivative is going to be this O prime of I times our I prime. Come over here, h prime of x. The derivative of the outside evaluated at the inside would be 1 over the natural log of 7 times 1 over 2x to the 4th minus 3x plus e to the x. And then times the derivative of the inside, which is I prime, 8x cubed minus 3 plus e to the x. Again, you identify your outer and identify your inner and come off to the side and find the derivative of each. That works, that's great. If that doesn't work for you, we would just need to go up to the top and say, okay, which of these 5 cases am I in? So 1, 2, 3, 4, 5. We're in 5, right? So we're dealing with log base b of a function. So the derivative is just going to be 1 over the natural log of 7, which is our base, times 1 over the function, times the derivative of the function. Okay, so whichever way you want to remember it, whatever works for your brain, use that method. Okay? All right, so 1, 2, and 3, our big picture is we have been dealing with a composite function. Okay? Now, if we're, again, being able to verbalize what it is we're dealing with, that tells us where to begin with our rules. So now, here in number 4, what is my big picture? What am I dealing with? A product, right? So we do see a composite function, but we see that we are dealing with a product of 2 functions. One of those functions is a composite function, right? So if we're looking at our 2 functions, 4x is our first function, and then this whole function raised to the 9th power is our second function. Okay? But before we go into finding our derivatives, let's do some rewriting. So last week we discussed there's certain things that we always want to rewrite before we apply our derivative rules. One is a radical. So we have the 5th root of x squared. Let's rewrite that as a power function. So the 5th root of x squared, that is x to what power? X to the 2/5, right? Because it's being raised to the 2nd power, but then we're taking the 5th root, which is the same thing as raising it to the 1/5 power. Putting those 2 together, we get x to the 2/5. And then we also want to rewrite anytime we have a constant divided by a power function, because if we didn't rewrite that 5 divided by x, when we got to the point of finding the derivative of that, what would we have to use? If we left it as 5 divided by x, we'd have to use the quotient. And we don't want to use the quotient rule if we don't have to. Okay? And so we want to rewrite anytime we have a constant divided by a power function. So 5 divided by x is the same thing as 5x to the -1. Okay, so now we see that this 4x is my first function, and then this whole function raised to the power is my second function. So I'm going to come off to the side, and now instead of identifying my O and my I's, I'm going to identify my F and my S. So my first function is 4x. My second function is 2 to the x plus x to the 2/5 plus 5x to the -1, all raised to the 9th power. Okay, so we need to find the derivative of each of those. We should be happy to find the derivative of 4x. The derivative of 4x is just 4. We need to find the derivative of s. But to find the derivative of s, what do we have to use? The chain, right? Because it's not x to the 9th power. It's a function of x to the 9th power. And so you could, off to the side, right, define your O and your I, but hopefully we're starting to get a little bit more comfortable. We're dealing with a function to a power, so we're in case 1. So to find the derivative of a function to a power, the power comes down in front, the function on the inside remains the same. We subtract 1 from the power, so the 9 comes down in front, the inside remains the same. So I'm just copying down that exact same function. We subtract 1 from the power, right? So what I have written right there, this is the derivative of the outside evaluated at the inside. And then we must multiply by the derivative of the inside. And we need to make certain that we put the derivative of the inside in parentheses. So I did that up above, but I didn't stress it. But notice that all of these here at the end, these are the derivatives of the inside. We need to make certain that we always put that in parentheses. Otherwise, order of operations, we're going to get the wrong thing. So if we're trying to find the derivative of the inside, we see the inside is a sum of functions. You remember from last week that we like sums, right? It's easy to find the derivative of a sum because we can just find the derivative of each piece. And so we find the derivative of each piece and leave the sign in between. Derivative of 2 to the x. It's very tempting to say that the derivative of that is x2 to the x minus 1, right? Because we've been using the power rule quite a bit. But 2 to the x is not a power function. right? To be a power function, the variable has to be in the base. When the variable is in the exponent, we're dealing with an exponential function, and we have to use the derivative rules for an exponential to find that derivative. So that would be the natural log of 2 times 2 to the x, plus the derivative of x to the 2/5. That is a power function, so we can use the power rule. So 2/5 x, and then we subtract 1. 2/5 minus 1 gives us negative 3/5. And then plus the derivative of 5x to the negative 1. That 5 stays out in front. And then we multiply by the derivative of x to the negative 1. Again, that's a power function. We can use the power rule. The negative 1 comes down in front. We subtract 1 from the power, so negative 1 minus 1 gives us negative 2. And then we close those parentheses. Yes. Yeah, so you can totally do that. Yeah. So the question was, why can't you just multiply the 5 and the negative 1, and you totally could do that. Yeah, so 5 times negative, this right here simplifies to just minus 5x to the negative 2. Okay, so then we recall that we're finding what we were doing, right? So we're finding the derivative of this g. G was written as a product of two functions, so we have to use the product rule. So if g of x is equal to f times s, its derivative is the first f times the derivative of the second, s prime, plus the second s times the derivative of the first, f prime. So if we put these all in here, f is 4x, and I'm going to put every component of the product rule in parentheses just to make certain that there's no issues with order of operations. So we have the first times the derivative of the second. So s prime is this whole long thing here. So I'm going to put brackets, all this in here. So 9 times 2 to the x plus x to the 2/5 plus 5x to the negative 1 raised to the 8th power times, open parentheses, natural log of 2 times 2 to the x plus 2/5 x to the negative 3/5. And then I'm going to rewrite that as minus 5x to the negative 2. Right, so again, this here is my first function. This right here is my s prime. So the first times the derivative of the second, plus the second, 2 to the x, so just s, 2 to the x plus x to the 2/5 plus 5x to the negative 1 raised to the 9th power. This is my s times the derivative of f, which is just 4. F prime is just 4. So here this is just f prime. Okay, so this is an example where we are using the product rule, but then when we get to the point of finding the derivative of our second function, we realize that our second function is a composite function, and so we have to use the chain rule to find the derivative of that composite function. Does that make sense what we did there? If not, ask a question. Is there any part of it that's confusing? Okay, so again, verbalizing what it is we're dealing with tells you where to begin with your derivative rules. Okay. All right, so let's look at another one. So we have f of t is equal to 3 divided by the 5th root of 7t cubed plus 2 to the t. Okay, so the first thing we notice is we are dealing with a radical. So we always want to rewrite our radicals as power functions. So this is 3 divided by 7t cubed right, so my mic just died. I just got new batteries. Can y'all hear me on Zoom now? There was something there. Okay. That was like a thumbs up, maybe. I don't know what it was, but something popped up. I guess that was good.
Yes, we can hear you now.
Okay, perfect. Thank you. Okay. All right, so we are rewriting this radical as a power function. So the fifth root of this function is the same thing as raising it to the 1/5. Okay. And then just like over here, where we rewrote 5 divided by x to avoid using the quotient rule, that same idea holds anytime we have a constant divided by a function raised to a power. All right, so as written here, we would technically have to use the quotient rule, but since we have just a constant divided by a function raised to a power, we can bring that up to the top and avoid using the quotient rule. So this is the same thing as 3 times 7t cubed plus 2 to the t raised to what power? Negative 1. Okay. And so then now the question is, do I have to use the product rule? No. Okay. What would make me need to use the product rule? Right, if I had a variable out in front here, right? If I had like 3t, then yeah, I'd have to use the product rule because both the two things I'm multiplying together are both functions of t. But since it's just a 3 out in front, I'm just dealing with a constant times a composite function. All right, so hopefully we all recognize that 7t cubed plus 2 to the t, all raised to the negative 1/5, is a composite function, right? And last week, I would have asked you to find the derivative of t to the negative 1/5. Now I'm asking you to find the derivative of this function of t to the negative 1/5. And so we would need to use the chain. Okay, so you can view it as just case 1 of the chain rule. Or if you want to, I'll do one more time of identifying my outer and my inner. Okay, so I'm going to view my outer as 3t to the negative 1/5. My inner I is 7t cubed plus 2 to the t. I need to find the derivative of each. So O prime, we have that 3 out in front, and then that negative 1/5 comes down. So we have negative 3/5 t. And then we subtract 1. Negative 1/5 minus 1 gives me negative 6/5. We find the derivative of the inside. Inside is just a sum of two functions, so we can just find the derivative of each piece and add. 7t cubed. T cubed is a power function. We can use the power rule. So that's just 21t squared. Plus the derivative 2 to the t. That is an exponential function, so we have to use the derivative rules for exponentials. That's the natural log of 2 times 2 to the t. Okay, so then we need to evaluate the derivative of the outside at the inside. And so we take our I and we plug it in for t in my function. That's correct. I want to point it. Okay. So we have negative 5ths times 7t cubed plus 2 to the t raised to the negative 6/5. So this here is the first part of the chain rule, the derivative of the outside evaluated at the inside. And then we need to multiply by the derivative of the inside. My derivative here would be negative 3/5 times 7t cubed plus 2 to the t, all raised to the negative 6/5 times the derivative of the inside, 21t squared, plus the natural log of 2 times 2 to the t. So again, this right here is the derivative of the outside evaluated at the inside, and then this right here is the derivative of the inside. Yes, Audrey.
Okay, so I just had a question. I was looking at this one. Why is it that the 3 to the negative 1/5 power, why does that relate to that specific section of it? And then the one for the problem before that, the to the 9th power, didn't relate to the 4x. If that makes sense.
Okay, so say that again. So the 3 to the negative 1/5, are you talking about like where I defined my O?
Yes, but yet for the one before that, the to the 9th power doesn't relate to the 4x. It goes with the second one in the parentheses. Because I was wondering sorry, I'm not really making any sense. For the fourth one, why the 4x to the 9th, why it's not 4x to the 9th, but instead it's 2 to the power of x, square root of 5x squared.
Okay, so I think I might be understanding, but I may not. So this 4x right here is staying there because my big picture on number 4 is the product rule, right? And so the starting point on number 4 is the product rule. And so we know to find the derivative of a product, we have to do this. And so we're going to have the first times the derivative of the second plus the second times the derivative of the first. Whereas on number 5, my big picture is I'm just dealing with a composite function.
Okay, so the product rule applies before you do the chain rule.
Correct. So
okay.
And I didn't write out all the details of the chain rule number 4. That could be another reason why it's looking incredibly different. But over here where I found the derivative, where I found S prime, we could have gone through and done exactly what we did down here and identified our outer to be x to the 9th, right? So if we wanted to, we could identify our outer to be x to the 9th and our inner to be 2 to the x plus x to the 2/5 plus 5x to the negative 1, right? And so we could view the overall answer on number 5 to be very similar to how we found S prime on number 4.
Okay, perfect. Thank you so much.
Any other questions? Okay. All right, so let's look at number 6. Okay, so if we try to verbalize what it is we're dealing with, what is my big picture here? What am I dealing with? Okay, so I'm dealing with the quotient rule and the chain. Okay, but the question is, where do I start? So are we going to start with the quotient rule? Are we going to start with the chain rule? Chain, okay? Because we're looking at the last thing that was done to form the function, right? So if I were kind of talking through the function, I would say we have 7x divided by 3x cubed minus 4, and then we're raising that to the 8th power, right? So we're starting with the last thing that was done to the function. And so here we see we have a function raised to a power, and so we're going to have to use the chain rule. So if we go through and identify our outer and our inner function, what would our outer function be? X to the 8th, right? Because we're taking this function and we're raising it to the 8th power. Our inner function would be everything inside those parentheses. So 7x divided by 3x cubed minus 4. Okay? So if we come up to the side and do what we've been doing on these problems, we take the derivative of our outer function, that would be 8x to the 7. We take the derivative of our inner function, we have to use the quotient rule, right? And so sometimes it gets a little bit much with defining everything, but let's go ahead and make certain we're good. So our top function would be 7x, and our bottom function would be 3x cubed minus 4. If we're trying to find the derivative, so if I is top divided by bottom, so, sorry. Okay. So if I is defined to be top divided by bottom, I prime would be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. I feel this cough drop is going to work great in just a minute, hopefully. Okay, so we need to find the derivative of each. T prime is 7. And then B prime is 9x squared. So plugging those in to the quotient rule, we would have B 3x cubed minus 4 times, I'm really sorry for those on Zoom. I'm normally better at remembering to turn off my mic when I cough, but sorry for coughing right into the microphone. Okay, so T prime is 7 minus T, which is 7x, times B prime, which is 9x squared, all divided by B squared, which is 3x cubed minus 4. Okay. So back over here, the derivative we were being asked to find, it was a composite function. And so we know it's the derivative of the outside evaluated at the inside. So we take our inner function and we plug it in for x. So O prime of I is 8 times 7x over 3x cubed minus 4, all raised, excuse me, to the 7th power. Okay, so my derivative is 8 times 7x over 3x minus 4, all raised to the 7th power, times the derivative of the inside, which is this whole mess that's over here. Big parentheses. 3x cubed minus 4 times 7 minus 7x times 9x squared, all over 3x cubed minus 4 quantity squared. I forgot it. right, so again, you don't have to go through and define everything out like we do to the side. You could instead realize I have a function raised to a power. That power comes down in front. The inside function remains the same. I subtract 1 from the power, and then I multiply by the derivative of the inside. Right? But to find the derivative of this inside function right here, I have to use the quotient rule. Okay. Questions on that? All right, let's look at the next one. All right, so number 7, what is our big picture here? Product, right? So we're dealing with a product of 2 functions. This 3x to the 9th is our first function. The 9 to the 2x to the 7th plus 4x is our second function. So we come off to the side. Our first is 3x to the 9th. Our second is 9 to the 2x to the 7th plus 4x. Find the derivative of each f prime would be 27x to the 8th. To find the derivative of s, what would I need to use? Chain rule, right? So last week we learned how to find the derivative of 9 to the x. We now have 9 to a function of x. I could go through and identify my outer and my inner, but I'm not going to take the time to do that. Just realize I'm in case 3 of the chain rule, so it's going to be the natural log of b times b to the g of x times g prime of x. So this is going to be the natural log of 9 times 9 to the 2x to the 7th plus 4x times the derivative of the inner function, which is, the inner function is 2x to the 7th plus 4x. So the derivative would be 14x to the 6th plus 4. Again, if you wanted to, you could identify the O and identify the I like we did above. Your O would be 9 to the x, and your I would be 2x to the 7th plus 4x. Okay? So if we come down here, the derivative, you have to use the product rules. My first function, 3x to the 9th, times the derivative of my second function, which is this whole thing, the natural log of 9, times 9 to the 2x to the 7th plus 4x, times 14x to the 6th plus 4. First times derivative of the second plus the second 9 to the 2x to the 7th plus 4x times the derivative of the first 27x to the given. So first times the derivative of the second plus the second times the derivative of the first. All right, so one more before we look at some applications. Or no, a couple more before we get to applications. All right, so m of t equals log base 8 of 5 plus 4 e to the t, all raised to the 9th power. So we're trying to verbalize our big picture here. What is our big picture? What are we dealing with? Chain rule, but we are dealing with, if we look at the outermost part, we're dealing with which case of the chain rule? A function, what are we doing to our inner function? Raising it to the 9th power, right? So our outer function would be x to the 9th. Okay? So we're dealing with a function raised to a power. Okay? Trying to decide if I want to write. Do you want me to write it out with O's and I's or not? Yes? O's and I's? Okay. Okay, so start here. We would identify our outer function as x to the 9th. And our inner function would be log base 8 of 5 plus 4e to the t. All right, and let me make certain I'm using the same letter, so I'm going to make that t to the 9th. Okay, so my outer is the outermost thing I'm doing, which is raising something to the 9th power. And then my inner function is the function I'm raising to the 9th power. Okay, so if I take the derivative, O prime would just be 9t to the 8th. I prime, to find the derivative of I prime, what do I have to use? Chain rule again. Right? So I'm not going to take the time to define that one with O's and I's because that would get really confusing between O's and I's. But just realize that log base 8 of 5 plus 4e to the t. That's case 5. So the derivative is going to be 1 over the natural log of b times 1 over the function times the derivative of the function. Okay. It's because we learned last week how to find the derivative of log base 8 of t. And so we have something inside here that's more complex than just t. Okay, so if we find I prime, this is going to be 1 over the natural log of 8 times 1 over the function, 1 over 5 plus 4e to the t, times the derivative of the function, the derivative of what I have underlined here. The derivative of the constant 5 by itself is 0, plus the derivative of 4e to the t is just 4e to the t. So really, if I wanted to, I could write that in parentheses and write 0 plus 4e to the t, but it would simplify down to just 4e to the t. Okay? So now to apply the chain rule to my original function, I need to evaluate my O prime at the inner function. So I need to take my I and plug it in for t in my O prime. So O prime of I. So I'm just evaluating this at I. So I'm plugging in I for every occurrence of t. So 9 times log base 8 of 5 plus 4e to the t. That whole thing raised to the 8th power. Okay, so this is my derivative of my outside evaluated at the inside. And then this is the derivative of my inside, which my inner function was a composite function, so I had to use the chain rule. So I'm using the chain rule within the chain rule because I am dealing with a composite of 3 functions, right? The outermost function is t to the 9th. The middle function is log base 8 of t. And then my innermost function is 5 plus 4e to the t. Okay? So I come back over here, m prime of t is the derivative of the outside evaluated at the inside, which is 9 times log base 8 of 5 plus 4e to the t, all raised to the 8th. Okay, so this is the derivative of the outside evaluated at the inside. And then we multiply by the derivative of the inside. Just for safety's sake, I'm always going to put that in parentheses. So that would be this over here, which is 1 over the natural log of 8 times 1 over 5 plus 4e to the t times 4e to the t. Again, that's the derivative of the outside evaluated at the inside times the derivative of the inside. Okay, so one more before we look at some applications. All right, so number 9 is written as a huge mess. Okay, and so number 9, if I try to take the derivative of that as written, let me try to explain what we are doing, right? we are dealing with the natural log of a function. And so we would start out realizing that we're dealing with a composite function, and we would need to find the derivative of that composite function. So we would take the derivative of the outside, evaluate it at the inside. So we take the derivative of the natural log of x, and we would evaluate that at this inner function. And then we'd have to multiply by the derivative of this inner function. But this inner function is this whole mess right here. And so to find the derivative of that inner function, I would have to see that I would have to realize that that is a quotient of two functions. And I would have to use the quotient rule. And then when I get to the point of taking the derivative of the top, I would notice that the top is a product of two functions. And so I would have to use the product rule to find the derivative of the top. But then when we get to the point of finding the derivative of the first and the second function in the top, we would realize that those are both positive functions. And so we would have to use the chain rule to find the derivative of each of those. Sounds terrible, right? You could be asked to do this, but not the way I just described. Okay, I would not recommend doing what I just described. What can we do instead? That's one choice. Okay, second choice. Say it again. Okay, so there's definitely ways that we can rewrite this. All right, and so the way that we can rewrite this is using our properties of logs. Okay, and so this is going to be very important to remember because you don't want to do what I just described, right? That sounds insane. And so we want to recall our properties of logs. Okay, so properties of logs. So these are properties that enable us to write expressions involving logs. So first one is the log of a product. Do y'all remember what we can do to rewrite the log of a product? We can separate them out and put what in between? Plus sign. So this becomes the log of A plus the log of B. And this works for any base B. I'm just being lazy and just writing log. Okay? Log of a quotient, A divided by P. Do y'all remember how we can rewrite that? So we can separate them out. What goes in between? Subtraction. Okay. And then the third one is the log of A raised to the power B. Do you remember what we can do with that power? Put it in front. Okay. So these are properties of logs that hold, and they have nothing to do with calculus, right? So this is ideas that you should remember from previous classes, right? These aren't derivative rules or anything like that. These are just properties that enable us to rewrite a log. Okay? And so you notice, for one thing, make certain that you don't use false properties of logs. So we can only do this. I'm just going to keep eating cough drops so I don't start coughing again. We can only rewrite things if a product or a quotient is inside of the log, or an addition or a subtraction is outside of the log, right? So there's nothing that enables us to rewrite a log if there's an addition or a subtraction inside of the log, right? So you have to know when you can use properties of logs and when you can't. Okay, so we do a lot of rewriting here. I personally would like to just write it all in one line, but I'll go step by step. But we have the natural log of a quotient, right? If we're looking at the inside there. So we can use property 2 and write that as the natural log of the entire numerator. So 4 times 3t minus 7 cubed. I'm also, at this point in time, going to rewrite that 6th root as being raised to the 1/6 power. So 4t plus 7 to the 1/6. So the natural log of the top minus the natural log of the bottom, so 5t squared minus 4. Right, so all I did there is use property 2, where my a is the numerator and my b is the denominator. So I separated it out into 2 separate logs with a subtraction sign in between. We then see that the inside of this log now is written as a product of 3 things, right? So we're multiplying 4 by this 3t minus 7 to the 3rd, and then we're multiplying that by 4t plus 7 to the 1/6. So we can use property 1, that if we're dealing with a product, if we're actually dealing with a product of 3 things, we can rewrite it as a sum of 3 separate logs. So the natural log of 4 plus the natural log of 3t minus 7 quantity cubed plus the natural log of 4t plus 7 to the 1/6. And then we already have this minus natural log of 5t squared minus 4. Okay, and then the first natural log and last natural log, there's no more rewriting I can do, right? Because we have a subtraction going on inside of a log, and there's no property that enables me to rewrite a subtraction on the inside of a log. But on the second and the third one, we have the entire inside of the log raised to a power. So we can only use this property when the entire inside of the log is raised to the power, like we have in the second and the third log, so we can bring that power out in front. So this becomes the natural log of 4 plus 3 times the natural log of 3t minus 7 plus 1/6 times the natural log of 4t plus 7. And then that last one remains the same, minus the natural log of 5t squared minus 4. Yes. Yeah, so I just took the power and it went in front. All right, so there is no more rewriting that we can do, but that's fine because it is way easier now to find the derivative of this, right? But keeping in mind when I'm using these properties of logs, I'm not finding the derivative, right? All I've done is just rewritten the original function. I haven't found the derivative yet. But now notice that we have a sum and difference of 4 functions. We like sums and differences. We can just find the derivative of each piece and leave the sign in between. So c prime of t. What's the derivative of the natural log of 4? So it's very tempting to say that. The natural log of 4. The natural log of 4 is just a number. So the derivative is just 0. Because it's not being multiplied by anything, right? It's being added by itself. And so the derivative of the natural log of 4 by itself is just going to be 0. Plus, we now have a constant times a composite function, right? We learned last week how to find the derivative of the natural log of t. We now have the natural log of a function of t. So we have to use the chain rule to find the derivative of this, right? The outer function is the natural log of t. The inner function is 3t minus 7. So this is just going to be 3 times the derivative of the outside evaluated at the inside. So 1 over 3t minus 7 times the derivative of inside. What's the derivative of the inside function here? 3, right? Because the derivative of 3t minus 7, it's a difference. We can just find the derivative of each piece. The derivative of 3t is just 3 minus the derivative of a constant by itself is just 0. Plus, likewise, we have a constant times a composite function. So it's just going to be that constant 1/6 times the derivative of this composite function, where the natural log of t is my outer function, 4t plus 7 is my inner function. So the derivative is going to be 1 over 4t plus 7 times the derivative of 4t plus 7, which is just 4, minus the derivative of the natural log of 5t squared minus 4. Again, a composite function, so it's going to be 1 over the function, 1 over 5t squared minus 4, times the derivative of that inner function, but the derivative of our inner function here is just 1. So that would be my derivative, which is much nicer looking than what I described in words we could have done initially. Yes?